motivate some specific signatures, mainly flavor observables. And in the third part, I'm going to talk about lepton flavor observables in G-2. So we know the standard model is complete. The Higgs boson has been discovered, and this is the last missing piece of the puzzle. And of course, beyond that, the LHC has probed a lot of potential new physics. And basically, the baseline conclusion is that there are no new states at the TeV scale or below that have a strong coupling to standard model particles. By strong, I mean like order 1 dimensionless coefficients. But we are less sure about very heavy states, of course, that we can't probe directly, or weakly coupled new physics. And more specifically, one can formulate this as a lifetime gap. What do I mean by this? I mean that the kind of particles that we can constrain on colliders are those that decay into something that is visible to the detector, right? And they have to decay in time before they leave the detector, because if they live long enough, they will leave the detector as some invisible signatures. If it's a heavy enough state, there are techniques like monojets and mono photon or whatever signature you can think of that can still be used to constrain them. But if it's too light, then it's almost impossible to see at a collider. So in terms of decay length, I used the example here of an axion-like particle that decays to 2 photons, or an axion, if you will. Now the decay length is inverse to the total width of this particle, which depends on the coupling and its mass. And you can see Atlas and CMS probe decay length in the unboosted state of a few nanometers to micrometers maybe. And then on the other end of the spectrum, if the particle is very long-lived, right, then you have cosmological constraints or astrophysical constraints. So if, for example, you have a light particle that can be produced in a star, in a red giant, and it is weakly coupled enough or long-lived enough to travel out of the red giant, then it completely changes the state of these objects. So the evolution of a red giant is very well understood because we have seen millions of them, and we understand very precisely how they lose energy. Now, if you have something that leaves the red giant in addition to neutrinos, say, it can carry away a substantial amount of energy, and that would change these equations. Same is true for supernovae. And then, of course, in between, you also have beam dumps. But there's a gap here. There's a gap between some micrometers and several kilometers of lifetime where these effects become effective in an astrophysical regime. And it's really difficult to probe this gap. Now, what kind of properties would a particle need to live in this gap? As I said, the decay length or lifetime is inversely proportional to the decay width. And that is a function of the mass and the interaction strength. So if you have weak couplings or small masses or both, that places you in this parameter space or this particle. Now, if you look at the parameter space that we have constrained for axion-like particles with couplings to photons. So on the x-axis here, you have the mass of this particle. And on the y-axis, you have the interaction strength with photons. And you can see that I've shown you here the contours of constant lifetime in this plane between 100 meters and a nanometers. And this is the kind of gap I'm talking about. So basically, the contours of the beam dumps and the astrophysical constraints, which extend to much lower couplings here as well, they are bound by this 100-meter decay length. And then above a nanometer in sense, or below a nanometer, you have the collider experiments that can probe this parameter space. Now you can ask the question, why would we even think about these particles? Because you would want to have some motivation. Why would a state be such that it has small masses or light couplings or even both? And there are theories, some theories in which it is not even motivated, but these are dependent conditions. So the particles being light and weakly coupled is basically the same statement in these theories. And examples of those are Goldstone bosons or new gauge bosons. And I'm going to use Goldstone bosons here for this talk to motivate this. This is a short review. Most of you will know what a Goldstone boson is. So if you have a global symmetry in some UV scale theory, in this case a complex scalar, then you can write that complex scalar as the magnitude of the field and the phase. And now if you break this symmetry with the mass parameter squared less than 0 in the Lagrangian, you'll find that you get a mass for this magnitude field, the Higgs mode here, and you do not get a mass for the exponent, right? So in this famous Maximum head potential, you can nicely illustrate this. So a mass for the magnitude means there is a, can you see my cursor at all?
Can you move it again? Yeah.
Yes, we see it.
Okay, so if this ball, this field in this potential tries to go along the real axis here in this picture, then it needs to fight against the potential well. This corresponds to a mass. If it goes to try around the circle, there is no resistance. So that is the massless mode in this picture. Because the Goldstone bosons, this A field, are the phase of a complex field, you can also formulate this as a protection by shift symmetry, right? So I can shift this field by some constant c and not change the physics at all, because all I do is I pick up a complex number that I can reabsorb again. So this symmetry clearly forbids a mass term, because a mass term, right, would give you an m squared a squared, and that a squared cannot be shifted without an effect, the a in this a squared. Also, it forces that all couplings that this particle has to standard model fields are suppressed by this scale f, right? So here, for example, the couplings to muons would be a dimension 5 operator, because you need the derivative to make this a shift invariant operator. And that forces you to have a suppression scale which corresponds to this scale f, the vacuum expectation value of this field I've just discussed. Now, exactly massless bosons are very problematic. If you had a very light or exactly massless boson with couplings to the standard model at all, you would introduce a long-range force that, depending on what the coupling structure is very strongly constrained. So a simple example is always say you have such a particle that couples only to electrons, and the force would extend between the Earth and the Moon. Then all the electrons of the Earth would have an additional force that only interact with the electrons of the Moon. And this part of the Moon would then give a different, feel a different potential, gravitational potential, if you will, than the rest of the Moon, which is something that is easy to detect in the movement of these bodies. So the global symmetry can still be broken, and can be broken by explicit masses or anomalous effects. Like in the case of the QCD axion, you have an anomalous breaking, but you can also just write down a mass term and consider this mass term to be the source, some external breaking source that is again suppressed by the scale f. So that is how, in the picture of this potential, that corresponds to just tilting the Mexican head, right? So you still, the mass that you produce for this particle is assumed to be small compared to the mass that is produced from the symmetry breaking. So this is an example where small masses and small couplings of this particle are basically the same statement, right? Because you have this underlying shift symmetry, both couplings need to be protected by the shift symmetry, and the mass, if it is an external breaking parameter, is suppressed by this as well. And therefore, this particle in principle this theory generates a light particle that has a small mass and a small coupling. The most famous example of such a Goldstone boson is the pion. In QCD, you have a large global symmetry, so you can rotate left and right-handed quarks independently, unless you turn on the quark mass, which breaks the symmetry. So you have a breaking, and you also have a spontaneous breaking from the QCD condensate. And now what you find is that the mass of the pion, which is the Goldstone boson associated with this breaking, is proportional to this external mass parameters and the spontaneous breaking parameter. And it turns out in QCD, it's an order of magnitude smaller than the masses of all the resonances. But this is an accident, of course, right? You can see from the equation that if mu and md were the neutrino masses instead, right? If they were much lighter, then this gap could be much bigger. So you can easily imagine that there is some new physics sector, and all the particles would be living at some scale that is given by the vacuum expectation value f, apart from one or a few particles that are protected because they are Goldstone bosons, and the mass gap is the result of a bigger difference between the external breaking and this underlying scale. The most famous example of this is, of course, the QCD axion, and that is also where the axion-like particles get their names from. So basically axion-like particles just means Goldstone bosons, a pseudoscalar field with a shift symmetry. But because the axion was the first such candidate, that is how this name became more common. So the QCD axion, most of you will know, was invented to solve the QCD problem. So you have the theta problem. So you have a CP-violating term in QCD that is the prefactor of g tilde that you can't completely rotate away. But if you introduce an axion or Pseudo-Nambu Goldstone boson that couples to this same operator, you generate a potential for this axion, and it happens that this potential minimizes that phase. So that would yield an explanation of why we don't observe this. But if you want to be more general, you should write down all possible interactions that such a field can have that are in agreement with these constraints, meaning the theoretical constraint that you want it to be shift invariant. And that means that you can have couplings to fermions, right, with a derivative coupling, to gluons, photons and Z bosons, or just Z bosons. And this, of course, in all generality, can yield a lot of different signatures. This Lagrangian has long been written down in the 80s, and many papers have been published to search for specific signatures of these axion-like particles. But I will focus on photons here because it's really hard to avoid photons. By that I mean that even if you try to construct a photophobic ALP, an axion-like particle that couples to something in the standard model, is almost unavoidable to get a coupling to photons eventually. So what I've written here in blue is the effective coupling of such an axion-like particle to photons. And you have a direct photon coupling in principle, they could be there, but let's imagine that is absent, this orange piece. Then you would generate it if you couple to fermions that are electrically charged, of course. You would also generate it if you couple to W bosons. And even if you couple to gluons, below the electroweak scale, below the QCD scale, there's going to be a mixing effect. The pion and the ALP are both pseudoscalars. They have the same quantum numbers, so they will mix. And because the pion likes to decay into 2 photons, the ALP inherits this decay, even if it just has a gluon coupling to begin with. So the point I'm making here is that it is really difficult to construct a model in which you don't couple to photons at all. It's kind of no matter with what you start, you will always have this effect. So how can you now close this gap? And I will use the axion just as an example for that. If you lose gauge bosons, like gauge bosons, for example, you will find a similar gap and you can have a similar discussion, but I want to motivate this at the example of the axion. And I'm going to discuss 4 different strategies to constrain the parameter space here that is so hard to probe at the LHC and with astrophysical observables. So the first is high statistics, then displaced vertices, exotic decays, and flavor observables. Now, what I mean with high statistics is clearly you can see that the parameter space that is constrained by LHC here is larger than the one that is constrained by lab. And one of the main reasons here is that you can produce more ALPs depending on their coupling strength, right? There's just a higher multiplicity of processes that can produce ALPs. And you can enhance that even if, for example, you have ion scattering, photon fusion and ion scattering isolates the ALP photon coupling, is enhanced by an extra factor Z because the ions have a large number of potential nuclei where the photon can attach to. And this enhancement allows you to eat into this gap. So what you see here is this little green parameter space is the green bound here. And Atlas has meanwhile performed this search and improved it over what I show here. This is a bit of an older plot, but you can see that this starts to increase the reach towards this parameter space. So this is one way of doing it. Of course, you can always produce more ALPs, and that would allow you to go further into this direction. The second is displaced vertices. And there's a very active program at the moment. So the LHC, of course, can look for displaced vertices. You can have an ALP that travels like a millimeter.
Can I ask you to go back to
yes.
that plot? I didn't quite get what's happening. So it's not just AA, right? It's AA plus luminosity.
Sorry, can you say again? It is?
The fact that, so what's this 10 nanobond inverse? This curve, yes, this dashed curve.
Yeah.
What is it?
You're right. If you increase luminosity, obviously you also get more events, right? So that is clear. If you have more, even if you have just there's 2 effects. You're right. Proton-proton collision with increased luminosity will start improving these bounds. But my point was, and that's not really my point, I'm pointing to the work of other people here, that if you use ion scattering instead, you get an additional charge square enhancement over what you get with protons.
Yeah, right. But there's a huge background there because the ions can break up, and
it's true.
So
it's true. That is partly what motivates this lower limit. You see, they have this hard cut at 5 GeV. So you need like this ALP here is on resonance. So you have to really reconstruct it to be sure that you constrain a new resonance and not being swallowed by background. Right. So you can ask the question here: why do these lines not extend further to the left? And what you just said is the reason. In order to suppress the backgrounds, you need to have it sufficiently heavy to see the resonance.
Thanks.
One more question regarding this.
Yes, yes,
sorry.
please.
So just because of QCD, it wouldn't I be able to also have a lead-A vertex? So for direct cross-section, is that much smaller compared to electromagnetic?
So here you assume that you only couple to photons, right? So you do not allow any other couplings at the moment.
Yeah, but that's sort of bizarre, no? I mean,
Yes,
what I mean by that, if I'm pragmatic and I know that this does have, at least at the quark level, if it has, so I could get into the nucleus level and I can have some sort of understanding of lead-A vertex, starting with the C gamma, or sorry, C glue sort of coupling like that. Do you have any intuition whether this is going to be subdominant compared to
I would expect
2D?
it to be. Well, obviously it depends on the hierarchy of the different couplings. If you turn C glue on, I would expect this effect to be more important than this, because this is really small, right? The fact that you can only constrain rather big couplings here is because this photon-photon fusion is severely suppressed. So if you turn CGG on, you would get stronger constraints from that, I'm sure.
Okay.
So yeah, I maybe should have said this more clearly. These bounds that I'm going to show now assume that you only have the photon coupling and no additional couplings. I will mention when other couplings are turned on, which of course makes sense, right? As it just said, that it's difficult to have an ALP that has just couplings to one specific particle.
Yeah, but this actually raises a very interesting question, because if you have a gluon coupling to gluons of this kind, then in extremely peripheral heavy ion collisions or even PP collisions, you might possibly get very hard jets. And that could be more easily detectable. There's very little background to it.
Yeah, that's a very good point. I would not be aware that this study has been done. I just want to add that all the other constraints on this figure that I show on the left here also assume that the gluon coupling is turned off, right? That would change things substantially. So for example, if you just look at supernova bounds, the fact that the ALP can leave the supernova for photon couplings of this size would be completely different if you have a coupling to gluons. It would just keep scattering off the nuclei in the star, right? And similar for other constraints here, like a beam dump constraint would also shift in this situation. So that it is a very good question. It's interesting. But as soon as you open up the parameter space, there's a bunch of different effects that you have to take into account if you want to compare this with other searches.
Great, thanks.
Now, displaced vertices is something that is actively been done at the LHC, right? It's actually cleaner if you have a displaced vertex. In particular, LHCb is very good at these searches. But there's a limit to this. So at some point, the lifetime is so large that the particle is going to leave the detector most of the cases, and then it's really hard to detect. Now, if you want to still probe particles with these lifetimes, you have to build an additional piece of detector material outside the detector with some distance to the interaction point. And there are quite a few proposals for this on the market at the moment. So Methuselah, you probably have all heard about, and the current status is still unchanged. So the plan here was, or still is, to build a huge barn of decay volume on Earth above Atlas or CMS, and then search for particles that travel all the way up there, shielded by the Earth in between, by the ground, and then decay in this volume. Codex B is much closer to the interaction point at LHCb, but it's the same philosophy. So here now you need some extra shielding in order to achieve that. SHIP is a beam dump experiment, so it's a different strategy, but has large, so would improve on the beam dump experiments. And Phaser is already in place by now. This is a tiny, like fridge size experiment, like tangential to the LHC ring that can probe particles produced in the forward direction. I want to use the opportunity to advertise our own proposal. So with Oleg and Christian and these people, we have proposed Anubis, which would be a similar experiment where we would instrument the Atlas service shaft. It has the big advantage that it's rather cheap. You already have the shaft in place, and you can put in detector plates here using the crane that is already there that has put the magnets in. And you could get this done for less than 10 million with a bunch of possible signatures that can be detected. And if you put in more than one plate, you actually have the interesting effect that some of them are shielded and some of them are not. So you have a good idea on how to estimate the background too. The status of this project is that at the moment we have funding for a prototype, which is being placed right here. So where the lowest plate would be. And hopefully this is all points towards this being done in time for run 3. If it works out, then I will have news on this soon, but this is the current situation. So this is like one of the other proposals in the already existing service shaft of Atlas. Now, if you use those searches, you basically do what the beam dump searches do as well. So if you go back to this figure, you can see that you would start eating into this parameter space from the left, right? You would start to make improvements toward the limits that we have from beam dumps anyways. The third strategy would be to look for exotic decays. And there we can take advantage of one thing that only the LHC can do, and that is produce Higgs bosons. Now I should say that this is different from the other two. Now here I do assume another coupling, and this is a coupling to the Higgs boson. Couplings between axions to the Higgs and the Higgs boson do not appear at dimension 5. Generally, the Higgs portal, the axion Higgs portal is dimension 6. And for the Higgs ZA coupling, there is a dimension 5 operator, but that is only in place if you have a coupling to standard model particles in the loop. If not, this is a dimension 7 operator. So they are suppressed, but because the Higgs is still, the invisible Higgs branching ratio is still very weakly constrained at the moment, you can get huge effects here. So what is shown in green here is the parameter space that you would probe if you have a tiny coupling to the Higgs and the Z boson, and only like a per mil of the Higgs branching ratio is given by that. So that is again different from the rest, but such a Higgs coupling would not substantially change the other constraints if it's that small. So exotic Higgs couplings, if these couplings exist, are a very powerful way to close this gap. And the experimental signatures are very different too. So if you have a low mass for the ALP and a small coupling, what you get is a boosted axion that decays into 2 photons in this case. And that looks like a H2Z gamma decay, because if it is very boosted, it is difficult for the LHC to disentangle 2 photons from one, right? Basically, if they hit in the electric calorimeter, they hit one cell, it becomes difficult. There's ways to do this, to measure the multiplicity, but it's difficult. So in general, what you would expect if the ALP is light enough is an enhancement of the H2Z gamma rate. There's no interference here. It always is enhanced because it is like a different final state. If you have medium mass and small couplings, you get the exotic signatures like H2Z gamma gamma, where you can search for the resonance in gamma gamma. And if you have a very small coupling, it becomes really interesting. That's one of my one of my favorite signatures is the Higgs would decay, say, into a Z boson and missing energy in the Atlas detector. And these are events that we currently just throw away because there's absolutely no way to determine that the Higgs is producing that Z boson if there's nothing else, right? It's just one other Z boson produced in the LHC. But if the ALP traveled away back to back and decays in some far side detector like Methuselah, you could actually reconstruct the Higgs and figure out that this was the original state, which is challenging because if you use Methuselah, for example, by the time that the ALP has traveled all the way up here with the speed of light, there have been already like number of 200 bunch crossings downstairs at the LHC. So you would need to keep these Z bosons, write them to tape, and wait for the other detector to tape to find a resonance in their data before you throw them away. So it should be very challenging to do that, but it's a very, very interesting signature to look for. That is all I'm going to say to exotic decays. Now I want to talk about flavor observables.
Sorry, and, Martin.
Yes.
Can you go back to your last slide?
Yes.
So this is, I mean, since we produce Higgs in beans with jets, in a sense that, I mean, this would be Z plus jets and MET. It's just an extra bean. Are you saying that there is no data in this thing right now?
No,
or we're
I'm
not
sure there
keeping
is
it?
data. I'm sure there is data, but the problem in discovering whether this is a new state is that I think the method you would get is really like the missing energy here is small to make a statement. I could be wrong. I'm not aware of searches in that channel. I think if you have like of the order of what you get here, like 30 GeV missing energy, it is really difficult to take this.
Large method comes in these window searches where you would get a similar mono Z plus met kind of thing. So okay, I understand. So it's the problem rather is the small met and multiplicity in like say Z plus 1 jet, but the small met.
Yeah, I guess at some point, of course, if the jet is hard enough, you get more.
Yeah.
But that reduces, I mean, the Higgs to Z A rate is going to be small either way, right?
Yeah,
as I said, it's like below.
Yeah, but the cross section of Higgs plus J, no? This monojet plus a Higgs. I mean, that's not substantially low compared to zero jet plus Higgs, right?
That's
might
true.
actually
that's comparable.
You might actually do
No,
better in
I'm saying
VBF.
Sorry?
You might actually do better in VBF, probably.
Yeah, that's also true. So probably VBF, if you don't have a far side detector, VBF is probably your best bet. If you the problem with the monojet, in my opinion, is that you're right that the rate is not too small. The Higgs production rate doesn't suffer much, right? But again, you would need a pretty hard cut. So I think you cut away a lot of events because you want a lot of like the jet has to be sufficiently hard for this to be disentangled.
Right. Yeah.
Okay. And I guess in that, I'm not sure, even in that case, would you be able to reconstruct the Higgs without knowing? So this could also be, yeah, I don't know.
No, it will just look like Z plus jets, and then you have a huge standard model Z plus jets background.
Yeah, what you would need to do is you would need to find, yeah, you need the A, I think, to reconstruct the Higgs there.
Yes, exactly.
Yeah.
Yeah, but thank you for the comment and the question. The fourth possible way is to look at flavor observables, and that might be less obvious than the previous strategies I have discussed. So let's first look at the ALP coupling in the quark mass eigenbases. So the couplings to quarks that I've shown before are different from these K matrices because you need to rotate. So these K matrices are rotated from the couplings in the original Lagrangian with the unitary matrices that give the CKM matrix, right? So that's why they have a different symbol here, and they also depend on the scale. In general, you have running effects, and they can be quite important. They're mainly important for the branching ratios of the ALP. And I want to mention this here because there has been a lot of confusion in the literature before the paper that we wrote, and only a few publications that had this effect included. But even if you only have couplings to leptons in the UV, you will get important couplings to quarks. And the main effect is the left diagram right here. So there's a top labeled on this loop, but imagine it's just a lepton, right? Then this loop still exists. And what this corresponds to is the mixing of the ALP with the longitudinal mode of the Z. So basically, in the same way the ALP can mix with a pion, the ALP can also mix with a pseudo-scalar Goldstone boson of the Higgs, which sits in the Z, right? And that is a way of how the ALP at one loop can generate couplings to quarks, even if you start with a lepton coupling in the UV. Obviously, if you couple to gauge bosons, you get this coupling as well. And there are the effects that you need to take into account. But if you have enough parameter space to run, then these couplings are all going to get generated. Now, there's a lot of potential constraints from meson decays that are sensitive to flavor of diagonal couplings, and they put really strong constraints on this suppression scale F. So let's just pick the strongest here in this table. Kaon decays to pions and invisible, right? This is only applicable for ALPs that are less than 200 something MeV. But you can see that the constraints points to a scale of 10 to the 9 TeV if such a coupling is present. However, this is only the case if this coupling is present at tree level. If you have a suppression, then this parameter space changes. And one of the tasks that we gave us when writing this paper is to compare these different constraints in the mass coupling parameter space if you turn one specific coupling in the UV. So loop effects will then generate ALP couplings that are flavor off diagonal the KD here, the MFV indicates that in the UV, we assume these couplings to be diagonal to begin with, right? So if you have such a situation, the first term would be 0. And then you get a bunch of terms that are induced by running. So this IT is an integral that takes into account the top coupling that I've shown before. And then you get a contribution from the loop when the coupling to the top quark is going to generate this, right? And you get a contribution of coupling to the W as well. And these are the two contributions that are most important. And if you don't start out with a coupling to the W, if you start out, for example, with a coupling to leptons, these are generated at higher loop order. So no matter what you start out with, running and matching effects are going to give you flavor-violating ALP couplings to quarks. That's an important point here. They will only occur to leading order in the masses to doublets, because for singlets, the standard model has no flavor violation. Basically, what happens here is I have a diagonal ALP coupling in the UV, but because the standard model has flavor violation, that induces flavor violating couplings for the ALP as well. For right-handed quarks, that is not the case. So if I don't start out with flavor violation in the UV at this order in the masses, I will not get flavor violating couplings at the scale of the measurement. So what I show you here is the parameter space that you can constrain if you start in the UV with a coupling to W bosons alone. So the ALP couples to the SG2 gauge bosons. It's not a QCD axion or anything. It just has this one specific coupling in the UV. And then you can constrain this coupling over the suppression scale F in this mass ratio by all these different constraints. You can see again the K plus to pi plus invisible constraint is the strongest if you are below like 100 MeV. And then there's a bunch of other constraints as well. If you go to larger masses, you have this bump here from the B meson decays, which are substantially cutting substantially in the parameter space. And then there are very weak constraints due to B mixing still for larger masses. On the right panel, this is compared with collider constraints. So the H to AA for 10%, 1%, and the per mil branching ratios is shown here in these dashed and solid lines. So this is the parameter space that you would constrain if you did this search for H to AA decays. And the gamma Z here is the total Z width that would also be affected if the Z boson had an axion in the loop or could decay into an axion and a photon, for example. Right, so this is the comparison between these flavor constraints. You can see that in most of the parameter space, they are much more important than these collider searches. I should also say that you might discover that in this plot, the final state can be very different. So of course, it can be invisible. That is the case when the coupling to photons, which CWW directly induces, is so small that it leaves the detector, right? So this ALP here will still decay to photons at some point, but it's too long-lived to be observed. Now the K to pi gamma gamma bounds here, you would expect, because again, the branch ratio to the photons is large. But for the B searches, it's K to A and then mu mu decays, which are branch ratios that are suppressed, right? They have to go through, you have a photon coupling, the photon goes to mu mu, and that dictates this branching ratio here. But they all appear at some point, right? There are EE constraints as well. And the BS-BS mixing is small because it needs 2 vertices with flavor violation of the ALP, right? So now you can connect to the question of how you close this lifetime gap. And you can see if I overlay this parameter space, the dashed contours here, with the flavor bounds from the slide before, right? So what's gray here on the right-hand side is just copy and pasted from the left-hand plot. And the colorful bounds here are copy and pasted from the previous page. And you can see that these indirect bounds, searches for ALPs in these B meson decays, they constrain precisely this gap. So there's a nice interplay between flavor observables and collide and astrophysical constraints, and in the sense that this gap is best constrained by flavor searches, if you will. That again does not assume that you have a different coupling like the Higgs coupling before, but now because we formulate the theory in an electroweak symmetric way, we call this C gamma gamma CWW, and it corresponds to C gamma gamma in the IR, and that's the main component. So that is this part of the talk. So I discussed 4 different strategies. You can try to go after this lifetime gap with large statistics, displaced vertices, exotic decays if they are present, or flavor observables. And all I think are well motivated. Again, I use the axion to motivate this and to illustrate this, but in principle, you can use any light weakly coupled particle, and you will find that these strategies are your options. Now, in the last part of the talk, I will talk a little bit about Flavour-violating couplings between ALPs and leptons. And those are slightly different. So what I do here in the first line is I just use the equations of motions to rewrite the couplings that are shift invariant in terms of pseudoscalar couplings. And there you can see that the scalar couplings vanish if the two masses are the same, if the two lepton masses are the same, right? And for the flavor off diagonal mass couplings, this is not true. So for the case of flavor diagonal couplings to leptons, you only have axial couplings, which is originally where the name comes from. This is also true for quarks, of course. But for flavor off diagonal couplings, that is not true. Flavor off diagonal couplings can be pseudoscalar or scalar. So for the flavor conserving couplings, I will define these quantities C mu mu, which are the differences between the right and left-handed couplings. And for the flavor-violating couplings, I will define C mu E, which are the magnitudes of both, right? So this is just the axial coupling for the flavor conserving, and the flavor-violating measures both. If I just turn on one, for example, only couplings to lepton doublets, I get both in the case of flavor-violating couplings. Similar to before, there are strong constraints. So I picked mu to E gamma effective. This is a decay where mu goes to E and a number of photons that cannot be reconstructed as different photons. And again, you see that the constraint is very, very strong. You get 10 to the 10 TeV constraint in this scale F. And if that is our constraint, that's basically, we don't need to hope to produce this thing elsewhere. We just need to look at this decay. But the situation is quite different than it is in the case of quark ALP couplings. Because in the case of lepton flavor-violating couplings, the standard model does not, the standard model conserves lepton flavor, right? So even if the ALP couples two Ws, it's not going to generate an off-diagonal flavor coupling. There has to be an internal neutrino. So these things are proportional to the neutrino mass squared over the W mass squared, and they're basically zero. So if you don't have in your underlying theory off-diagonal couplings to leptons, the running will not induce them. Well, they will only induce them proportional to neutrino mass over W mass to some power, which is completely negligible. But if they are present, if these couplings are present, they are not the only source of flavor-violating transitions. You also have dipole moments induced by these couplings, right? As soon as you turn this vertex on, you get also the diagrams in the lower row here that give you dipole moments. And now you can say, well, the dipole moments are loop suppressed, so why would I care for them if I have these tree-level couplings as well? But you have to be careful. There is always a second vertex, right? So if you look at mu to 3e and you turn on this off-diagonal couplings and you have an ALP coupling to electrons, then from this tree-level diagram, you get something that is suppressed. This process is going to be suppressed by the electron Yukawa. That's also true for scalars, of course, but for the ALPs, this is a very powerful suppression. And if you had a dipole up here, you lose a loop factor. But because the exchange particle is a photon, you will not pick up a Yukawa coupling. So basically, it's the hierarchy between loop factor over Yukawa over QED coupling. So the dipole is always going to win here. The dipole diagrams are more important for mu to 3e if you have an axion-like particle than the tree-level exchange for that reason. Now you get constraints from these dipoles, because if these couplings are present, you get mu to E gamma, for example, induced by these dipole moments, and you also get anomalous magnetic moments like delta and mu that are flavor conserving. So that is interesting. Maybe one can connect the two. Let's have a short look at the anomalous magnetic moment of the muon. You all know that this disagrees with the standard model for some time now. The Brookhaven result gave a tension of just under 4 sigma. The Fermilab result that has been published last year is going the same direction. It's slightly closer, but if you combine the two experiments, you get an over 4 sigma discrepancy between the standard model prediction and the experimental average. Well, I should add there is some discussion here because it depends on how you determine the theoretical prediction. We can talk about that, but for all intents and purposes, let's consider this tension for the moment. Now, if you want to get a feeling of how big this effect is in terms of potential new physics, you can look at the standard model. So the standard model contribution that you get here, like this is not suppressed by the neutrino mass because it's a flavor conserving transition. The standard model gives you a contribution of about 400 times, the electroweak contribution from the standard model gives you about 400 times 10 to the minus 11. That's pretty much the order of magnitude that you would need, right? And that is a good way to estimate what kind of new physics you would need. You could have something heavier than the W, but in order to get an effect of that size, that means you need a sizable coupling, right? So you can't go far in this direction. You can, of course, overcome this chiral suppression here. So this is proportional to the muon mass squared over W mass squared. If you have something exotic like a leptoquark, where, for example, in the best case, you have the top in the loop, you can replace this by n top square over n W square, or over the lepton mass square, leptoquark mass square. And in this case, you can pick up quite an enhancement factor, but still, it kind of, if you don't want to get to non-perturbative couplings, you can't get much about a few TeV, right? So your new physics, if it's heavy, has to be of the order of a few TeV, even in the best possible case, to give an effect large enough to explain the anomalous magnetic moment of the muon. So that to me is a motivation to also look in the other direction. If the new physics in the loop is light, then this could also work with a small coupling. So we come to the question of whether the axion can explain this. Let me just shortly mention there's also a deviation in the electron anomalous magnetic dipole moment. And this has been reported 2018, I think, for the first time. This is a new measurement of the fine structure constant. And if you plug this into the theoretical prediction for the anomalous magnetic moment of the electron, you find discrepancy of 2.4 sigma in the original measurement in cesium. And in the meantime, there's a second measurement I should also not forget to mention. That is the same mechanism. You measure the fine structure constant, this time in rubidium, and this now seems to go in the other direction. So for the electron anomalous magnetic moment, the situation is quite, any of these discrepancies is small either way, and it's not quite clear that there is a discrepancy that is worth looking at, because these two measurements disagree with each other. I should also add the rubidium one disagrees, like the group that published the rubidium measurement disagrees with their own measurements from a few years prior. So in my opinion, it's a bit more questionable, this result, than the first one. But I want to just give you an overview here, and now use this as a motivation to look on whether an axion can be an explanation for either, or maybe even both of these anomalies. Now, let's start with a situation where you do not have Flavour violation. If you have an Axion-like particle without Flavour violation, you get two possible contributions. You get a contribution from the axion in the loop, like in this pinkish diagram, and you get this green diagram where the axion is in the loop, but it's also connected to a photon. The first diagram is a contribution in the wrong direction if you want to explain the muon anomalous magnetic moment. So the sign here is negative. It is fixed because you proportional to the magnitude squared of this coupling, and the loop function has the wrong sign, unfortunately, as well. So you don't get a resolution from this diagram alone. The second diagram, in principle, can have either sign, because if you have muon coupling and a photon coupling, and it's the interference of these two that gives rise to this contribution. So basically, if you have a photon coupling large enough such that this effect is bigger than the first, this could explain the muon anomalous magnetic moment. For the electron, I will, for the rest of this talk, use the opposite sign. And if that is where the case, then the first term alone could yield an explanation. So I'm going to disregard this rubidium measurement for the discussion here. Now we can look at the parameter space that you would need to go to explain this. We choose the muon coupling to be negative, and we turn on a large electron coupling as well. And then you can explain the muon anomalous magnetic moment, this orange region, and the yellow region, you can explain the electron. And in the overlap, you can potentially explain both, if this anomalous magnetic moment result for the electron is true. And the reason is that such a large coupling to electrons and muons induces a photon coupling big enough to give this effect. So I do not need to turn on a separate photon coupling here. It's basically built in from the loop coupling of the ALP to two photons. But you can see that you need sizable couplings, and the couplings need not only be different in sign, they also need to be very different in size. So you need very large lepton flavor non-universal couplings if you want to solve that problem. You can go back to the parameter space in this plot and see where this is. So if I want to show the region where the g-2 of the muon could be explained, is this red parameter space here. And you can see it's almost ruled out, like a little bit falls into this lifetime gap, but for most of the parameter space, it is not possible to resolve this with universal couplings. Now, in our publication, we asked the question, what happens if you turn on Flavour off-diagonal couplings? And then the situation changes. We do not use this photon diagram, but we use a diagram where the axion mediates a loop where you have another flavor in the loop. And what's interesting here is, depending on what flavor in the loop appears, you get a different behavior of the loop function. So if you have something in the loop that is heavier than the lepton outside, you get this, this greenish contribution, which is again, can be of either sign. And if whatever is in the loop is lighter than on the outside, the leading term is fixed in sign again, but it has a negative prefactor, right? Now you can, looking at this, it is very reasonable to ask whether you can get both from tau couplings, right? If you turn on a tau mu and a tau e coupling, do you get an interesting contribution to both? Right, and that is true. You would get both, but you would also get a mu to gamma e decay mediated by the same couplings, and that completely rules out an explanation where you turn on tau couplings. So if you want to explain both anomalies, it cannot go through tau couplings. It's just impossible because you get a constraint from mu to e gamma mediated by the same couplings that is too strong. If you instead turn on just a coupling to muons and electrons, you can get both, because again, the contribution that you get from muons outside and electrons in the loop is different from the contribution you get from electrons outside and muons in the loop. And here's the parameter space for which you can resolve either or both, shown in a plane where I just show you the couplings for different axion masses. Right, again, 100 MeV, GeV, or 10 GeV. So that could resolve these anomalous magnetic moments in principle. Now, what I show you here are different constraints on the mu-e couplings from the table I showed you before, and where this parameter space would allow for this resolution, and where it is already ruled out. So it's a bit more busy than the previous plot. What we cannot do here is what we did for the quarks. We cannot say we start with some diagonal coupling in the UV, and these are the constraints in the IR. Because again, for leptons, if you start in the UV with diagonal couplings, you won't get any flavor violation in the IR. So you need to turn on at least two couplings. And we allow for C mu E. This is the coupling that mediates between a muon, electron, and an ALP. And we turn on some diagonal couplings. And we always choose the largest still allowed couplings in the corresponding parameter space. And now you can see there's a bunch of different constraints. There's constraints from mu to E going to invisible, mu to E A gamma, muonium oscillation constrains it very weakly. And for higher masses, you get mu to E gamma and mu to 3E constraints as well. And you see in this parameter space, both the contribution to the anomalous magnetic moment of the electron and to the muon is completely ruled out. So you won't be able to explain it for these parameters. However, again, we have chosen diagonal couplings here to be very large. So this might change if we choose different values. And these plots show the same constraints and contours as before, but now we fix the mass and vary the diagonal coupling. Right? So diagonal coupling to leptons is down here, and the mu-e coupling is here. And if you have a very light axion, you can only explain delta AE, and only if this mu-e coupling is very small. If you have heavy ALPs, you see that there is some parameter space where you can explain either or the other, but you can never explain both. The parameter space where they overlap is completely ruled out in either case. So the bottom line of this discussion is that axions with flavor off-diagonal couplings are capable of explaining anomalous magnetic moments of leptons, either the muon or the electron, but it is not possible to find parameter space where you can explain both at the same time. And that might be good because it's not really, it doesn't look like the electron anomalous magnetic moment has a large discrepancy eventually. So let me conclude. I want to motivate you that ALPs are harbingers of new physics sectors that can live at some high scale, and it might not be directly accessible by collider searches. But if we find these Axion, these Goldstone bosons of these broken symmetries, we can learn a lot about this sector. Their couplings are set by the symmetries of this new sector. So even if we don't discover them, these new particles directly, we might still be capable of using these measurements to learn what this new physics sector is. And flavor searches are important to constrain the symmetry structure. You would need them on more than one measurement, ideally to reconstruct what you have in the UV if you take the RG running into account. And in principle, you can also use these ALPs. They could be the reason why the muon anomalous magnetic moment is in tension with the experimental measurement. And that is, with that, I conclude my talk, and thank you again for your attention.
Thanks, Martin. So Nishita has a question. Go ahead.
No, I was just clapping.
Oh, that was a clap. Sorry. Yeah. Any questions? So I had one question which is sort of technical on page 34-ish. So basically you showed that the couplings to, for example, quarks could be a pseudo vector or vector, but the vector one comes with only, is it easy to say why this one comes with only Mi minus Mj? Why is 0 in the isospin symmetric limit, for example?
If you use the equation of motions, you can directly see this. Like you have to move past the gamma 5 matrix or not, and that picks up a sign in the couplings. It's just that usually people call the axion because it only has these axial couplings, but that is not true if you have Flavour violation. It's only true if the masses are the same. Yeah,
that's what is a little bit counterintuitive. Okay, I see. One just has to work it out. Okay, any other questions? Okay, if not, then thank you, Martin, again, and hopefully we'll see you in person sometime.
Yeah, that would be great. Thanks again for the invitation. It was fun. See you.